Good afternoon. Today is October 27th, 2025. Tele 1022 Telecommunications, Bencher College, London, Ontario. Okay, here's the timestamp. All right, so today we're going to take care of, we're going to scratch the surface of the wireless signal propagation. All right, this slide here is titled laser. Where's my laser? Come on. There we go. Conservation of energy. Well, it's part of it. Electrical energy must be converted into the electromagnetic energy in order for the energy to propagate in free space. Well, yeah, when we're talking about propagation, we're not going to talk about the coaxial radio guide. This is when we're dealing with space here. So propagation is associated with the word space. All right, since air is a good insulator, electromagnetic energy can propagate in the same way as an electrical conductor like copper or aluminum would conduct electric current. And the air being a good insulator is the key. We can also have electromagnetic radiation in the space as far as vacuum is concerned. Okay, what's the next bullet say? Much like an audio speaker, okay, here, much like an audio speaker that converts electrical energy to sound pressure waves, longitudinal sound pressure waves. An antenna converts electrical energy into electromagnetic energy. Okay. In both cases, the speaker or the loudspeaker, properly called, and the antenna are referred to as transducers. And as far as we remember from the telecommunications model of any type of a telecommunications model, for the most part, the input and the output would be a transducer. What is a transducer? A transducer is a device that converts one form of energy to another. Example, a microphone converts air pressure waves into electrical signals, and a loudspeaker does the opposite. It takes the electrical energy and it converts that into sound waves, right? Air pressure waves. So transducers, antenna, and the speaker. Okay, so we took care of the transducer thing. In any wireless system, we need to have both a transmitting antenna and a receiving antenna. Make sure you write this down. All right. Well, it's true. Right. Wow. You get your money's worth here for this course. Now, the existence of radio waves was predicted mathematically, right, in the mid 1800s by someone whose name was James Maxwell. And when I hear that name and I hear the word equation associated with that, wow. All right, 1800s. All right, electromagnetic waves continuing. An electromagnetic field is made up of, okay, so electromagnetic field is made of electric field and a magnetic field. These fields exist with all electric circuits. You build a circuit on your breadboard, you are going to have electromagnetic field around it for sure. Some of them is going to be stronger, some of them not as strong. With the magnetic field surrounding the conductor and the electric field present everywhere, there's a potential, well, voltage difference. When there's voltage, there's electric field. And when there's current flowing, there is going to be magnetic field spinning around the conductor. So that should not be anything new to you, but we're getting somewhere with that. In most circuits, the field energy is returned to the circuit, and the energy consumed by the circuit is transferred to the load. Like, for example, inductor would just build up a field, energy field, and it would collapse onto itself, and that energy is returned into it. So you can say that, in short, Lineman's term, every circuit breathes energy, right? Breathes in and breathes out, just like we breathe the air. All right. So let's say in most circuits, the field energy is returned to the circuit, and the energy consumed by the circuit is transferred to the load, with some losses in the transmission. Yeah, of course. We have to puncture through the air, we have to puncture through the resistive elements of any kind of conductors, and so on. The law of conservation energy must be obeyed. Nothing lost, nothing gained. Right? Now, if all the energy in the fields is not returned to the circuit, we call this a radiation. This type of radiated energy is typically not desirable. Well, typically is the key word, but can be difficult to eliminate. Where there is, what was it? When there, where they cut the forest, the wood chips fly. That's what somebody smart said. It is referred to as electromagnetic interference. Okay, let's go again here. If the energy in the fields, electrical and magnetic, is not returned to the circuit, as the circuit quote unquote breathes, we call this a radiation. Some energy escapes. We call it radiation. This type of radiated energy is typically not desirable, can be difficult to eliminate, and it is referred as EMI. We talked about that last time we saw each other. Electromagnetic interference. It also commonly refers as noise. It's also common as noise. Man-made noise. Virtually all electronic devices with some clocking circuits will radiate. A computer has a clock. It goes by the clock. Everything is synchronized by the clock. Things will radiate. Your keyboard radiates. Your mouse radiates. Your electric shaver, although it doesn't have any clocking circuitry, it is going to radiate as well. Everything radiates. It's just how much of radiation is allowed to escape. It is also, believe it or not, it's controlled by Industry Canada as well, or in Canada, and everywhere else, as the law of the land dictates. If the source of the radiation is another transmitter, it usually is referred as radio frequency interference. So we have two terms here: electromagnetic interference and radio frequency interference. Both of them are interferences, but one of them is a electromagnetic EMI, and the other one is RFI, radio frequency interference. Sometimes EMI and RFI are used interchangeably, especially when the true source of noise is unknown. What some of the examples of EMI or RFI? It just so happens that I do have that thing in next slide. All right. Examples of EMI and RFI. EMI, noise created from let's say, alternator in the car. Noise created by a laptop. Talking about EMI, electromagnetic interference, excluding the in-band Wi-Fi. So, noise created by a laptop, but not the Wi-Fi thing that laptop has, right, or utilizes. Noise created by the overhead power wires. Noise created by electric motor. um, electric dryer, and so on. Now, here's the RFI, interference caused by a distant radio transmitter. So here is just a general noise of the electronics working or the electricity working. And here is intentional radio frequency transmission that interferes with some other transmission. So RFI, radio frequency interference caused by a distant radio transmitter, noise caused by an out-of-band emissions on a transmitter. The transmitter drifts, or somebody doesn't know what they're doing when they're transmitting, then some of the frequency can overlap and interfere with, or maybe the radio stations are too close, but all that, as I said, is being regulated. What else? A noise caused by mixing products of multiple transmitters. We have multiple transmitters in the area. They will start some of the carrier frequencies and whatever they transmit, they actually can, they're too close, and the frequencies are too close or too close to the specific type of frequencies, they might start mixing with each other unintentionally. So that would be a radio frequency interference. Interference caused by Wi-Fi transmitters on the same channel. Interference caused by signals from two cellular transmitters on the same frequency. That can that would be interference. Many of the above can be difficult to source and reduce or eliminate. So things get a little bit complicated quite often. Although, don't be alarmed and scared, because when next time you pick up the phone, you won't even think about it. You're going to have a pretty clear transmission and receivage on your cell phone. So, more examples of EMI or RFI. EMI, static noise from an electric motor, interference from power lines, switching power supplies. Switching power supplies can create noise. Yeah, there we go. Lighting, fluorescent lighting was bad. Now it's less and less of it now, but still. Spark plugs in car engine. So that's EMIs. EMI. Radio frequency interference, a cell phone, Wi-Fi signal. Static on a radio due to nearby broadcast tower. Okay. I'm not going to go too much into that. A microwave oven causing interference. That could be radio frequency interference, although microwave oven could probably be more included in the EMI rather than RFI. However, the food is being heated by microwaves. So although it's not like a radio wave, but it is a radio wave. Well, not a radio wave, it's a wave, all right? It's a microwave of a specific frequency. Two-way radio signals disrupting another device. Yeah, that could be. There was a time that in audio industry, pro audio industry, and you're talking about something like 15 or 15 plus years ago, all the wireless microphones systems and any kind of wireless device, the guitar jacks, they had to be retuned on the account of the cellular networks expanding. So cellular networks needed more bandwidth, and some people sit down at the table with some other people and they say, well, we just have to do that drastic cut, so we have to do it. So it caused a lot of headaches sometimes. If somebody did not get my wireless microphone retuned, they will be running a risk of something cutting in while they are performing into their wireless microphone, and usually that would not be a voice. It would be some sort of very, very intense and harsh noise, not very pleasant to the human ear. All right, just because so well, I mentioned the power supplies, switching power supplies. Um, I just when I was going through the slides early today, I said, "Well, maybe I can throw this in as well." It's a bit of a digression, but not as much. This shows what's going on with the power supplies, linear or switching. So, okay, what did I say here? Linear and switching power supplies differ in primarily in efficiency, size, noise, and cost. Linear power surprise, linear power surprise. Larger and heavier, and the linear is also less efficient. So the amount of energy it consumes to the amount of energy it gives. Oh, look at that! It's a low efficiency, 30 to 60%. But produce very clean. That should be comma. Low noise power. This should be one line here. Ideal for sensitive application like audio or medical equipment. Okay, so yeah. Now switching power supplies smaller and lighter, more efficient. The efficiency goes up, but they generate high frequency noise and it's a complex design. If you want to know more, look at this. Look at that. Oh, here. Yeah, here's a link. If you want to expand your knowledge on this topic here, I'm not going to play. That's I found a YouTube video that pretty much explains things about those type of things. All right, let's go back to electromagnetic waves here. Now, we are unable to see electromagnetic waves because they're way out of our human visible spectrum, part of the spectrum. In the diagram below, here's below and here's the diagram. The electric field E is shown as being perpendicular to the magnetic field H. Right, so here's the H, here's the E. This one goes up, this one goes to the right. This one goes down, this one goes to the left. But they will be perpendicular to each other. All right. Again, in the diagram below, the electric field is perpendicular to the magnetic field in the electromagnetic wave. Yeah, see? Interesting. The direction of propagation is perpendicular to both E, and so the direction of propagation. So this thing goes that way. That's the direction. Again, that way. And it is perpendicular to either this or that, of course. And these two are perpendicular. So everything is perpendicular. Should be called perpendicularification wave. Oh, electromagnetic wave. Okay. All right. So now we got that picture out of the way. Here's a reference if you want to know more. Well, reference to the book if you want to buy. Okay. Now, I've thrown in today also one more slide in this presentation here. Wave front. Here is the source of the wave, and this, of course, by looking at this old-fashioned school bell. This device here, it's a handheld device, makes a sound, and it makes waves. So here's one wave of the front, wave front here. Here's another wave front. Here's another wave front. And anywhere around, it could be considered as a wave front. So there will be wave front 1, wave front 2, and so on. And somehow you can see that the waves propagate 360 degrees from the isotropic point source. Isotropic point source. It's a source which is an isotropic point. Here's a wave front, another wave front, and next slide explains what characterizes something that's called a wave front. Hmm. Here comes the next slide. All right, isotopic point source. And here's the wavefront. We'll get to it. Isotropic. And I just kind of made the text with different shadings so you don't get lost in this whole blob of text. Right? Isotropic, meaning a physical property of having equal value in different directions. Just hang on to that for a second. An isotropic point source can be used to describe an electromagnetic wave that is radiated equally from a point source in a free space. So here is you drop the pebble in the water, uh, and the waves start in all directions equally from that isotropic point. We can define a wavefront as a surface joining all points of equal phase. So if the wave from here propagates and just reaches peak here, all those waves are going to reach the peak here, reach the peak here, reach the peak, and so on. So that would be all those waves that reach the peak in phase. And the next time they reach the peak, there's another wavefront. All right. So here's a wavefront. And from isotropic point, this whole thing just extends 360 degrees. Since the wave travels at the same speed, well, okay, hold on. Since the wave travels at the speed of light, at some point, in-phase energy will have reached a point on a sphere, because this is not a 2D circle, it's a sphere 3D circle. Again, go back. Since the wave travels at the speed of light, at some point in the phase energy in-phase energy will have reached a point of a sphere wavefront 1. Boom. A second wavefront, twice the distance from the center, can be shown. So far, so good. Since the area of a sphere is, here's the formula for the area of the sphere. It's 4 pi r squared, okay? We can say that the power density on the second sphere will be quarter that of the first wavefront. You might have to kind of look at that and read it 100 times and roll it through your mind. But we're not going to stop here. This is given by the following power density formula. Here is the formula. Power density, okay, at any given point is the total power, which would be the power that has originated in the transmission here. It's just that the total power is being dispersed around the wavefront and travels. And as it travels, it gets weaker. You see here? That r squared, it's on the bottom of the equation. So the longer the distance is here, the smaller the number is going to get, right? Right. Whereas PT is the total power, and power density unit is watts per square meter. Sip of coffee. Example, and I used some colors here. What's the signal power received in 100 square centimeters area? What's the signal power that could be contained with 100 square? Remember, we're talking about radiation here, right? And so things are happening in space. What's the signal power received in 100 square centimeters? So we know how big the area is that contains the power. Located 5 kilometers from a 10-watt isotropic point source. So this here transmits 10 watts, and the distance, wherever it is, let's say it's here, it's 5 kilometers from here. And we want to know what would be the power contained within 100 square centimeters. All right, so we have that formula here. Power density equals total power divided by 4 pi r squared, which is our distance. So the power is in watts. Okay, good. Now we just have to convert the centimeters to meters in order for this formula to work properly. And we have the 4 pi times 5,000, because 1 meter is 1 kilometer is 1,000 meters, so 5,000 meters. And if you do the calculation here, 10 over 4 pi 5,000 squared, you're going to get 3.18 times 10 to the negative 8. And what's the unit? Remember, watts per meter squared. Okay, but so now we have the sort of the answer yet, but we need to know how much power, how many watts we have in that 100 centimeters squared area. So 100 square centimeters equals 100 divided by 10,000. You just have to do that 10,000 thing here. So that's going to be 0.1, 0.01, sorry, square meters. So we must multiply the answer by 10 to the negative 2, which is the blue colored here, and that's the blue color. That's why we're converting that number here into this one here. So 3.18 times 10 to the negative 10. Add that on here, or add the multipliers. So then we have 318 to the negative 12. So here, 10 plus that gives it here. So we got 318 picowatts. Radiated power. So here's the answer here, over 100 centimeters. Okay. So radiated power drops off as inverse square function. We have it on the, next slide explains that. Powerful transmitter, that means that the powerful transmitter produces a weak signal when at a significant distance. The signal drops fast. So, and I put this thing in red. Safety is an issue here. With a high power transmitter, because you need a high power transmitter to transmit signals so it's usable at certain distance. And you're talking kilometers. Or sometimes hundreds of kilometers. So safety is an issue, because if you get too close to the transmitter, you're actually going to get hit with with the energy. So some of that was not really taken under consideration during the World War II times when there would be technicians working on the new thing that was invented was called the radar, and the radar would be part of the radar system would be a transmitter that would transmit high powered signal, and some of them would be microwave transmitters, and people were not paying attention to the safety issue of that as they worked on those things, and well, some of them got burned pretty badly because you can see that some of them became, well, they lost their eyesight and so on. So um, standing beside a transmitter is not that good idea, or the transmitter antenna. So let me read this thing here. Safety is an issue with high power transmitters, including microwave transmitters, especially microwave transmitters, which use high gain focused parabolic antennas. Radiation burns can be serious. And I remember when I was in college, we did have some labs with actual microwaves being involved. We had to enter a Faraday's cage. We could walk in there, and we had to perform a couple of labs, but those labs were strictly supervised by the professor, so we didn't get hurt, because you could get hurt pretty quickly just by manipulating the circuit while it's on, and you having your hands too close in there. You could get your hand burnt. Just bring ketchup and mustard, because you can have some hot dogs, might as well. No, but things were serious. So radiation burns can be serious. And since most electromagnetic waves are not visible to us, we need to take extra precautions when working with. So your biggest weapon against being hurt in this case is your knowledge. Okay? And of course, well, don't get close to that. So, okay. So when we said this here, radiated power drops off as an inverse square function. So I saw that in the original presentation. I thought maybe we should, excuse me, we should add on something, because just having that one line, throwing it at you and moving to the next slide, I don't think it's fair. All right, so radiated power drops off as an inverse square equation, inverse square function. Again, radiated power drops off as an inverse square function. This is a principle known as the inverse square law. Okay, I'm not going to branch off from that one now, because that's going to take forever. As you move away from the source, the intensity of the radiation decreases rapidly, because the same amount of energy is spread out over a larger surface area. Remember the wave fronts right here. You move away here, but the total energy that was transmitted, it's not just at that point, it's spread all around here. So over here is going to be less losses, because look, the circle is smaller. All the total energy is within here. You go far away, further away, the total energy is around here, and so on. Get the idea. So as you move away from the source, the intensity of the radiation decreases rapidly, because the same amount of energy is spread. I think I have a sneeze coming on. Spread out over a large surface area. Okay. For example, doubling the distance from the source reduces the radiated power to 1/4 of its original value. Continuing, imagine a sphere rotating. Okay. Remember, we see that as a circle. This is not a circle, it's a sphere in all directions, top and an angle on the other side. So that one point, you're just getting that energy that is dispersed around that wavefront that goes in all the directions. Like how many directions? It's 360 times 360 degrees directions. Uh, Imagine a sphere radiating energy from a point source, isotropic point source, as the distance r from the source increases. The surface area of the sphere, which is the 4 pi r, increases as the square of the distance. All right. Yeah, you see, that's where the square distance is. Since the total power is constant, the power per unit or intensity must decrease proportionally to that kind of ratio here. And here's the reference I included from the from this little thing that I got. You want to know more? Click on this. All right. Waves not in free space. We're going quicker than I thought we would today. On Earth, wave propagation is impacted by our environment. Well, yeah. Even wind can affect that, right? And there are several effects that impact the propagation. There are several. All right. Several parts of several, okay. Many things can affect the propagation that have to do with the environment, okay? Got it. These are similar to those that affect the light, with which is also electromagnetic wave that just happens to be in the visible spectrum for us humans. So if there is a fog outside, the light is going to have tougher time punching through the fog. So for the other electromagnetic waves, radio waves, there are other elements that act as the fog would act on light. The three categories. All right, we distinguish here reflection, refraction, and diffraction. I'm not sure if you had the network systems with me, or you're going to have that maybe next semester with my colleagues. I know it's not going to be with me because I know I'm getting another subject. You're going to talk about the fiber optics, and fiber optics have to do with the light propagation. And we're going to be talking about reflection and refraction. Well, with the electromagnetic waves, we have another guy in town here. That is diffraction. Okay, let's move on here. Reflection. Much like light, radio waves can be reflected by a medium. For the total reflection, the wave must be perpendicular to the medium. Typically, the medium absorbs some of the wave, so we do not see 100% reflection. If the light source, if this is the medium here, the light source hits and it just bounces back. Okay. And when we do not have the perpendicular angle to the surface, the some of the light is going to reflect, and some of the not light, some of the waves is going to refract. Refract, which means it's going to puncture through the surface and change the angle. That's refraction. That's if both mediums have, well, different type of refractive index. I'll only write that down. For angles other than 90 degrees, we are going to see a reflection where the angle of incidence, the angle of attack, is equal to the angle of reflection. If the wave is parallel to the reflective surface, the electric field can be shortened or shorted severely attenuated if the surface is conductive. Right? Again, if the wave is parallel to the reflective surface, we're not talking about light reflection. With the light, you get something that's called a critical angle, which means the light is not going to either reflect or it's not going to refract. It is going to travel along the surface. So if the wave is parallel to the, so you're going to actually lose the transmission. You can lose the transmission. So remember this, what we just said here. Refraction. Refraction occurs when the radio waves, and we're talking about the radio waves now. Refraction occurs when a radio wave passes from a medium of one density to another. Part of the energy is reflected, and part of the it's transmitted through, for example, the water, if this is water, if it enters from the air to the water. So this would be bounced off, reflected energy, and this energy here punches through the surface and continues, but at a slight different angle because of different densities of the air and different densities of the water. So this is refraction as opposed to reflection. Now, what's this thing here? Diffraction. A radio waves traveling in a straight path can be, well, it can bend around obstacles. Light also demonstrates that property. So that's, that will be forever discussion of is light waves or is light particles. What was first, chicken or the egg? All right. So, and it actually displays both characteristics of a wave and particles. So radio waves traveling in a straight path can be bent around obstacles. This is based on the principle that each point on spherical wavefront can be considered as a secondary wavefront, as a source for a secondary wavefront. That's how electromagnetic waves behave. The area lacking coverage is called a shadow zone, and here is all the visualization of that. Diffraction examples. We can see that the obstacles can present a significant issue for the coverage. So here's a transmitter, and here's a mountain. Here's bird's eye view, and here's the, I think they should call it the horse's eye view. So the mountain can cover. Now, the waves at some point can bend around the edges here because remember, see that? Yeah. Each point can serve as a secondary wavefront or a source of a secondary wavefront. So then this thing is going to become a secondary transmitter and it's going to start transmitting, and that's how it works. Okay. Now, but there would be a bit of a shadow zone where there's no coverage. Is this really an issue in the real world systems? Well, yeah, because if all of us right now that are becoming addicted to using the cell phone, and if we find some ourselves in that, well, in this area here, well, maybe we won't be able to use our cell phone to do our Facebooking and all that kind of stuff for about 10 minutes. And that could create a huge psychological, you know, hopefully reversible damage. But there's nothing that a good therapist couldn't solve. However, on the serious note, here's the shadow. Now, is this real issue? Well, yeah, because what if you need to have the receivage there? You need to be able to receive those waves for whatever reason. Right? What are the potential solutions? Well, one way would be make this antenna higher. And if you're going to have line of sight and make this antenna higher, well, so height can do that. There's some other solutions. Well, it just so happens that the next slide has some of the answers. Solving the coverage issues. All right, or issues. There are many ways to address coverage issues. By design, cellular network architectures or many adjacent cells can address the issues related to obstacles. So here's a telephone network, and by wires, by radio guide, for example, or maybe by radio waves too. We have a cellular network designed in a way that if one antenna doesn't see you, another will. Antennas can be oriented to address specific coverage areas. Now, more difficult solutions require radio repeaters. Radio repeaters is another way of doing things. In, well, remote areas, forget the cellular here. You're going to have a radio station or a radio transmitter that is going to be seen by this antenna, and it's going to take that signal, repeat, and pass it on to another antenna and receiver and the system, and repeat that, and so on. And if you are having like a portable radio with you, you're going to connect to the same antenna that repeats your signal, goes there. Repeater, it repeats signal. Other challenges created by below ground tunnels. Okay, well, you're driving from Windsor to Detroit or from Detroit to Windsor. You can take the bridge, you can take the tunnel. Well, the tunnel is underwater. It's covered by a lot of things, a lot of concrete and a lot of water. You think the radio waves are going to penetrate that? Not a chance. So that could be an issue. Even basements or certain buildings. All right, let's just read that line again. Other challenges created by below ground tunnels or basements might need dedicated, potentially costly solutions. So yeah, you can have it, but it's going to cost you. Reflections in our environment can often work to our advantage. So that's the next couple of slides. The reflections are going to be here, okay? So don't worry if you were worrying about that. Now, in building coverage issues, often, more often than not, actually, large buildings have coverage issues, particularly the ones in the core of the building, the areas. The worst area is elevators, which have concrete shafts, hard to penetrate by the electromagnetic waves. There are modeling tools and or site surveys, and it can cost just to do the survey with the modeling software can be costly, thousands of dollars. There are modeling tools and or some same as there are modeling tools for rendering the acoustics of a church arena, conference room, and so on. So there are modeling tools and surveys that can be done to determine the magnitude of the problem. In this image, the green is good, red is bad. Bad means no coverage. See here? That would be the elevator shafts for the most part. Talking just about, for example, the cellular coverage. But how is it that you walk in, you go to Toronto, to some of the large buildings, London, Ontario here too. You go into the elevator, your phone works. Okay? Um, we'll address that. Now, reflective coatings on windows, they could be conductive, and conductive materials would block the waves. So reflective coatings on windows of the buildings make the situation worse. The solution will require a will require direct base station feed or off-air pickup of signals. So the signal is going to be picked up, not by the air, to feed an internal distributed antenna system, DAS. Not sure where you're going to end up working. If you end up working in any kind of communication companies, you might have to design those systems. Extremely popular solution that is implemented in hospitals, business high rises, and in large buildings. It costs money, but you don't even know. You're working with your cell phone, you got the coverage there because it's a form of a repeater. This can be quite costly, and it's often priced as dollar per square foot. Often, there's more than one cellular service provider, and the need for public safety. So there are those DASs and triangulation systems and whatnot. It all works in the building. So quite often you're going to be installing a lot of WAPs in the ceiling all over the place. WAP stands for wireless access point. Yeah, we do have a lot of wireless access points in our college. That's how you're going. That's the Wi-Fi boxes that are in the ceiling and on the walls everywhere, that you can log into your Wi-Fi signal with your laptop or your cell phone. Funding for in-building coverage is a significant issue. Who's responsible for that? Well, whoever law of the land says it is possible. All right, let's look at the wave propagation. There are 4 different modes for the propagation of radio waves on Earth: ground waves, space waves, and sky waves and satellite communications. So sky waves and satellite communications are kind of under one category. 1, 2, no, 3, 4. So yeah, there are 3 kinds of people in this world: those who can count and those who can't. All right. So the most significant factor in determining the mode used is frequency. Ground waves. Ground waves must be vertically polarized. Did we have that? Remember this slide here? Since the E field is vertical in here, in this point, then this wave is said to be vertically polarized, which means the antenna sticks up in the air. And it could be one part of the antenna goes up and down, and then there's insulator, and then there's other part, or sometimes the ground is being used as the other half of the antenna. If you have antenna here's a transmitter that transmits the waves that is vertically polarized, it is a good idea to have a receiving antenna somewhere that is also vertically polarized. Then you can get the most benefit out of that. This electric field is going to hit the antenna in such a way that is going to create a wave here, right? In the same way, if you polarize the antenna vertically, you're not going to have, you can actually lose the transmission. So in that case, you need to have a horizontally polarized antenna so it transmits the E fields that way. And of course, magnetic fields associated with that would be perpendicular to that. So yes, it's important how the receiver antenna is positioned with reference to the transmitting antenna. All right. So ground waves. Ground waves must be vertically polarized to prevent shorting to Earth or to Earth's surface. The E fields will be perpendicular to Earth. If you have the E fields parallel to Earth, the Earth is conductive and it can short the E fields. Here's the Earth. Let's say the Earth is flat. Okay. Here's the antenna transmitting the E field. So with in the Earth the E fields are going to travel along. If you have an antenna that is parallel, then because the Earth is resistive or conductive, all those E fields are going to be shortened by the Earth. Yeah. That's as simple as that one gets. So these are the ground waves. Again, let's go back to here. Ground waves must be vertically polarized to prevent shorting to the Earth's surface. Now you understand why. This type of wave is attenuated by the Earth's surface as it travels at the best of times, at the best of situations. And this increases the significantly with frequency. So the Earth is going to attenuate the wave that is set up properly, the antenna vertical. Still, the Earth is going to attenuate the wave. And the higher the frequency, the more attenuation you're going to get to the point that it's pointless to transmit. The maximum frequency for the ground wave is 2 megahertz. However, most communication uses lower frequencies like 30 to 300 hertz. Primary applications, submarine communications, and obviously because of the limitation on the frequency, it's a slow speed transmission. But sometimes that's the only thing you can use. All right, space wave propagation. This is the most commonly used mode of radio communications. The propagating wave is transmitted directly from the transmitting antenna to the receiving antenna. Now, as far as polarization, the antenna system, I'm talking about transmitting antenna and the receiving antenna, they have to be synchronized as far as positioning. But the polarization can be either vertical or horizontal, which means still, if you have a vertically polarized antenna, which means it's perpendicular to the surface of the Earth, the receiving antenna also has to be perpendicular to the surface of the Earth. But if the antenna is parallel to the surface of the Earth, the receiving antenna also has. But you can use either or system. You can decide. So that's what it means. Polarization can be either vertical or horizontal or both. Space wave now. Still, most terrestrial communications, and what does terrestrial mean? Terrestrial as opposed to extraterrestrial describes items that are associated with the land or the planet Earth. So communications within planet Earth. So most, can you have extraterrestrial communication? Well, yeah. How do you think the satellites work? Well, or how do you think Earth is communicating with the space station? All right, let's go. Most terrestrial communications, like broadcast radio and television, cellular, public safety communication, telemetry, and Wi-Fi uses this mode. One of the downside of this mode is that it's mainly limited to the line of sight. Mainly. And that's a huge mainly. Again, one of the downsides of the space wave propagation, as opposed to ground wave that we just covered, is that it has to be line of sight. So antenna has to see the other antenna. Problem with that is that the Earth is not actually flat, believe it or not. Actually, I think the Earth is concaved because when I walk, my shoes are worn on my toes and on my heels the most, so the Earth must be concaved. Yeah. Apologies. All right. You see here what happens here? The antenna transmits, it broadcasts the waves, and the waves are always going to hit the Earth here. And that is going to become a secondary isotropic point, and that thing is going to start transmitting. So there could be some issues due to the reflections. There could be some echoing happens because this distance is shorter than this total distance. For the most part, things are not happening with problems here. Okay, so one of the downsides of the most that's mainly line of sight. In some cases, there might be a reflected wave that can cause issues, which is what I just talked about, as it will have delayed phase, echoing, ghosting. Increasing the transmitter and or receiving height is one way to increase the transmission distances. So height is important. For most cellular systems, this is not an issue because you have a bunch of cells, and cells have antennas, and they're within the distance. So for most cellular systems, this is not an issue. And in fact, the design objective is often to reduce the transmission distance to keep the cell size small and maximize the frequency use. So we looked at the ground waves, space waves, and now we have the sky wave, propagation. Right. This method is often used for long distance transmissions. The transmission uses a reflection from the Earth's ionosphere. All right, here's the Earth, here's the atmosphere, and above that, there are several layers of ionospheres. There's a layer of ionosphere and there's a stratosphere, but ionosphere can, and I was called ionosphere because it's a sphere surrounding our Earth, and it's in the shape of more like, technically it's a sphere, but I'm not going to get into we're not going to split the hair over that. And the ionosphere is a layer that covers the whole Earth, so it's a sphere, and it's made out of ions, so it's called ionosphere. And those ions can reflect electromagnetic wave and bounce it back to Earth, and reflect again and bounce it back to Earth, and so on. So you could pretty much send a signal and wait for that signal to bounce off the whole Earth and come back to you in a few seconds. Now, not that many seconds. Quite short period of time. All right. Dedicated. Okay. All right. So here, the downside of the characteristic. Okay, no, we're getting ahead of ourselves. The transmission uses reflection from the sky, from the Earth's ionosphere to increase the distance. So yes, You could, yeah. In fact, every 11 years, there's an extra layer of ionosphere, which is a bit higher, because every 11 years, the sun has increases its activity, producing ions. So that's every 11 years, things are hotter than usual. And that's when we have to recycle because we have to save the earth. So every 11 years, the sun creates, because of increased activity on the sun, it's just 11-year cycle, creates extra layer. And some of the frequencies can puncture through the ionosphere, but they get hung on and reflected from the second layer, where they can travel further distance. It used to be a big problem when most of the communication was analog, that there would be a police station or police car receiving a signal to go to street so and so address because they need to respond to a call. And they would try to find that address. They couldn't find that address. What are you talking about? Well, sometimes it would take them a couple seconds to figure out that this police car is in London, Ontario, and whoever is trying to communicate with them is in Montreal, because of that every 11 years. I don't see too many possibilities of that problem right now, as far as the analog communications go. Well, we have digital communications right now, for the most part. The downside of the characteristic is the ionosphere. Oh no, hold on. For the long distances, skipping can be used to cover thousands of kilometers. Skipping. Right. Got it? Reflecting. The downside of that, the downside is that the characteristics of the ionospheres are not constant. This is all the time, at all times, evolving, changing. The ionosphere takes a different shape, different strength, different height sometimes, different intensity, and sometimes it disappears, and other layers appear, and some layers disappear. So the downside of the characteristic on the ionosphere are not constant, and there is considerable variation from day to night. Dedicated frequencies are also needed for that. So frequency reuse can be limited when it comes to covering more distance. Like, for example, there could be radio station transmitting on certain frequency, and if the other station is far enough, it can also transmit on the same frequency, because those distances will not cover each other. But when it comes to this type of skipping thing, well, some of the frequencies can interact not in a desirable way, or mix. Dedicated frequencies are also needed, so frequency reuse can be limited, which is an issue when high density communication is needed, such as cellular communications. Satellite communications. This method provides a reliable communication with the well-defined signal paths. With geostationary orbits, a geostationary orbit is a specific type of orbit around Earth where the satellite appears to be motionless from a fixed point on the ground. So with geostationary orbit, it is possible to cover much of the Earth, through the satellite communication. The cost to manufacture, launch, and maintain is quite high. However, this is offset by benefits. So the benefits outweigh the costs when it comes to that's why your bill for your cell phone is what it is. Applications for cellular satellite communications include GPS, television broadcast, wireless, pretty much everything. Okay. At some point can be transmitted using satellite. Well, not everything, but it can be. Weather has minimal effect on satellite communications. However, high moisture content or heavy rain can reduce the signal strength. So sometimes, yes, you lose a television signal or internet signal, or depending where you are. For many long distance applications, satellite communication is superior to the skywave. However, it does introduce, introduce longer propagation delay. Sorry, that end should not be there. Due to the uplink and downlink paths. A propagation delay is the travel of the signal from one end of the device or system to the other end of the device or system. Like, for example, the TTL, gates, chips, inverter, and gate or whatnot, they do have propagation delay. And if you have a lot of them in series, that propagation delay can actually trip your circuit communications. So because of the distance between Earth and wherever the satellite is, and it has to come back. So it's going to take, however, when I'm talking to Europe, I feel almost like we're talking real time. So the technology has gone quite far to accommodate that. Although, if you're trying to have a band practice with people at different points of Earth, or different locations, then you're going to see the significance of the propagation delay. You just won't be able to, because some people say, yeah, we can do that, technology, and they try to do that, and it doesn't work because there's a delay in things. What this means, that means this is the last slide here. We're going to tackle those. Let's tackle them. So I'm not going to go through the questions here right now, so we could go over next time we see each other. It's going to be on Friday. See how much we remember that, and we're going to enforce the retention of the material that I'm giving you right now. Like, for example, we know what the difference between EMI and RFI is, but I'm going to remember that week from now. Okay. So that's it for today. It is, what day is it, kids? Did I teach you that? What day is it today? What's the best answer for what day is it today? Matthew said Monday. I don't like that answer. It is Monday, but see how much better it sounds when we say it's almost Friday, because every day is almost Friday. It's just some days are more almoster than others. So with that attitude, put a smile on your face. Have a great rest of the week, and I'll see you. I'll see you during the lab, and then I'll see you on theory on Friday. Thank you, and have a good day. Have a good day as well. Thank you.